In the last video, we learned about continuous probability distributions in general, and we realized that we were going to be focusing on two common continuous probability distributions, the uniform distribution, which is rectangular, and the normal distribution, which is bell-shaped. In this video, we're not going to focus on the normal distribution yet. Instead, we'll be looking more closely at the uniform distribution. So notice that we have a few points to consider here. Uniform distributions exist because some variables have possible values that can occur equally likely. So the probabilities are evenly spread. This leads to a probability density function that is a straight horizontal line. Okay, so this would be your PDF there. At a height above the x-axis, which is equal to the uniform probability, meaning that whatever the probability is for each and every value, that's the height of your horizontal PDF. It extends across the range of all possible x values, resulting in a rectangular shape. Okay, so for this example here, we see that the random variable could take on values anywhere from 2 up to about 8.9, and infinitely many possibilities in between those 2 points. And since all of these are equally likely, you see the horizontal PDF creating a rectangular shape when you close it down to the edges. Total area of any normal distribution's larger rectangle must equal 1. This forces the height of the rectangle to be the reciprocal of the range. So notice in this example, the range is the maximum 20 minus the minimum 0, giving us a distance of 20 as the base of the rectangle. So if base times height equals the area of a rectangle, and it does, then when I multiply this base of 20 times the height, I need to end up at 1 as a product. The only way to get 1 when multiplying something is to multiply it times its reciprocal. So the height has to be 1 over 20. When we multiply the base times the height, there is an area of 1 for this bigger rectangle. Let's find the probability that a random variable will fall between 4 and 15. The probability of a value falling between 4 and 15 is the area of the smaller rectangle between 4 and 15. It has a base of 15 minus 4, so 11 is the base. The height is 1 over 20. So when we multiply those together, we get the answer 11 over 20 as our probability. Here's another example. The image shows the probability of a value falling below 2. The area of the smaller rectangle will give us that area. So we take the base. The base is 2 minus 0. That's 2. The height is still 120. So when you multiply those, you get 2 times 120 is 2 over 20, reduced to 1 over 10, or 0.1. Here's another example using the same setup. What would be the probability of a value being less than 15? Pause and think about it. Too late. Probability that x is less than 15 equals the base of 15 times the height of 120. We get 15 over 20, which reduces to 3 over 4, 4.75. Now, the green region is the probability of falling between 20 and 15, or 15 and 20. And since two of these regions complete the entire big rectangle, we know that when you add these two together, you'll get 1. Or in other words, if I subtract 0.75 from 1, this green region would be 0.25. But if we use the base times height approach, let's see if we get that answer. The probability that x is greater than 15, I would take my base, which is 20 minus 15 equals 5, times the height of 120 equals 5 over 20, which reduces to 1 over 4, or 0.25. Right, so notice they do add up to 1. Here's another example where the range does not start at 0, it starts at 8 and goes up to 23. So our base of the larger rectangle is from 8 to 23, giving us a range of 15, or a base length of 15, which forces the height to be 1 over 15. The probability that x is less than 12, we would get the base of this green rectangle. 12 minus 8 gives us 4. 4 times 1 over 15 gives us 4 over 15. The probability of that should have been a greater than symbol actually. Oops. So this should be turned around because we're now doing the probability that x is greater than 12. Notice that I didn't bother to mention the 23 because the maximum it can even be is 23, so it's good enough to say greater than 12. So greater than 12 would be the base 23 minus 12, which gives you 11. 11 times 1 over 15, so we get 11 over 15. Now the normal distribution, we can't use the same approach of base times height because notice that if we did that here, we'd have a rectangle that was too big and we would get a probability that was too large to represent the probability of a value falling between 1 and 2. So for normal distributions, you could use calculus. Most of us haven't worked with calculus at all at this point in your education. So rather than using calculus, you'll be using tables and technology to figure out the areas of these regions under the bell curve. In the next video, we're going to start looking at z-scores. See you there.